Hello and welcome to the DECTRIS lunchtime seminar. I'm glad to see so many happy and friendly faces coming to our seminar. And today we are going to present to you the latest POLLUX detector, our new detector for laboratory applications. So, let me get the pointer going. We have put together for you an attractive agenda, so we split the presentations in 4 parts. I'll give a brief introduction to DECTRIS, to those of you who are not familiar with us, and to show you what we are doing today. Then Markus, the product manager for X-ray analytics, will actually introduce you to the new POLLUX Panorama high resolution and what that means and how it improves the resolution for your lab systems. Then we have a guest speaker on stage. This is William Boyer from Proto, we are glad to welcome, who will show you about Proto and POLLUX. And then towards the end we have our new colleague Hans Gildenast, who is our new application scientist. We are very happy to have him since a year at DECTRIS. And he will address suppression of fluorescence in a challenging application example. With this, let's get started. Now, I'll give you a brief introduction, only a couple of slides about DECTRIS and what we are doing and what we are doing today. I'm Tilman, I'm product manager focusing on the high energy detectors. And I've joined DECTRIS 16 years ago, and that was when the Pilatus was actually the first hybrid pixel detector that just had spread and made a big impact at the synchrotron facilities. It really transformed how people were measuring their data, getting higher quality data with this photon counting technology, and much faster. Yes, and we are still doing that. So what is our aim? We provide cutting-edge detection technologies and powerful digital software solutions that integrate into your workflows, into your beamlines, into your laboratory setups. And with this, we serve both academia and industry engineers. And I have just one impact slide with which I'm most familiar. I chose that one. That was also yesterday presented by Andrew Beal. And the diffraction computed tomography being much enhanced by our detectors, where you get the chance nowadays to look into things like a battery, time-resolved, cycling the battery, and see with chemical specificity how the particles, how things inside the battery are changing. And with the newest detector generation speeding up, providing thousands of diffraction patterns in a couple of seconds, you can now get much better time resolution, see more, get more insights, right? And I need to mention this beamline has already last year been upgraded now, even with the next version. This was still done with the Pilatus 3. So, one too quick. Just some quick facts about DECTRIS. We are a Swiss privately owned company. As you can guess, we were founded in 2006, so we celebrate our 20th anniversary now. And we are located in Baden, so that's about 3 to 4 hours drive from here. And we have offices in the US and in Japan and work with distributors in Asia. We have a staff now of about 190 employees, of which most are at the headquarters in Baden, where we do design and production of the detector systems. And we have the luck to have all the things you need for producing and designing the systems in-house. That means we are strongly R&D focused, with 2/3 of the company staff holding a university degree and working in development or engineering of the things. We can do hardware, firmware, software, and most essentially, we can design the readout ASICs in-house ourselves. And the readout ASIC is where the detection really for each pixel takes place, the processing of the event that your detector is recognizing, detecting. With our clean room, we have the chance then to take these readout chips and do this, what we call the hybrid. We of the hybrid detector, we need to merge the readout chip with the conversion layer, which is also a semiconductor device. And this we do in this clean room. Then these modules go to our assembly and production hall, and we build the detectors of different sizes from these modules to get you smaller or larger active areas on the devices. And then we have a couple of X-ray setups for calibration of the devices to provide you with fully calibrated detectors. Now I come already to my last slide. We are empowering scientific discovery and now I want to focus more on the different fields or markets we work in. So we started, as I said, in the synchrotron, and soon after we started deriving systems from the synchrotron systems for laboratory applications that would go into the diffractometer or the strain and stress setup. And a couple of years ago, we also started to transfer this technology and make it available for electron microscopy. For example, for STEM, this is now a game changer with the ARENA detector we are providing. And later edition, like about 2 years ago, we came to think, how can we help you processing all the data that you get from this massive data that you get? And that, of course, is a bit of an issue to process it. Developing a scientific data platform that helps you process and collaboratively work on that. But for today, I'm finished, and Markus will take over to present to you the POLLUX detectors. And I would like to point out as a last thing, the POLLUX is not something that we have derived from a synchrotron device. This is something where we have made a dedicated development, a new readout chip specifically for laboratory applications. With this, I'd like to thank you for your interest in the name of the entire DECTRIS team. And yeah, Markus, please come up on stage.
Yeah, thank you, Tilman. Thank you all for joining us in our seminar and spending your lunch break with us. I'm very happy about the opportunity to introduce to you today our latest member of the POLLUX family of detectors, the POLLUX Panorama High Resolution. DECTRIS POLLUX, yet another detector from DECTRIS with a strange name. Where does it come from? Some of you may know POLLUX as a demigod from Greek and Roman mythology, or as the brightest star in the Gemini constellation. However, of course, we named POLLUX after a mountain in Switzerland located close to Zermatt. And our POLLUX detectors have exactly this aspect ratio as you see here. And in addition to that, there is also POLLUX Panorama with a wide aspect ratio that allows you to capture many peaks in a single frame. This is how the POLLUX detectors look like, in case you haven't seen them yet at our booth. And POLLUX features an active area of 19 by 14 millimeters, POLLUX Panorama of 58 by 14 millimeters. The 14 millimeters are a great match for the line focus beam size, so you capture your full diffracted signal. And with the 19 millimeter of POLLUX, you get still a large area for this class of detector, while the detector is highly compact and can be used in portable instruments or in benchtop instruments. It's great for scanning XRD and residual stress. And POLLUX Panorama gives you, of course, a Y2 theta coverage, so it's great for stationary measurements to follow phase transitions or for even fast duct scans and such things. Our POLLUX detectors are 2D pixel detectors with 75 micrometer pixel size, so they offer the same great 2D resolution as our Eiger-2 detectors. And for many measurements and applications, this is ample of 2D and spatial resolution. However, when it comes to best possible 1D resolution, what sets the benchmark here are our own Mythen 2 detectors with a strip width of only 50 micrometers. And of course, with POLLUX, we want to improve on Mythen 2 on every relevant aspect. And that is why we are launching now POLLUX Panorama High Resolution with a dedicated high resolution sensor and a pixel size of 37.5 by 150 micrometer. And this way we redefine 1D resolution with all the versatility of a 2D pixel detector. So how does the POLLUX family of detectors look like now with this latest edition? We have POLLUX and POLLUX Panorama with 75 micrometer square pixel size and a pixel array of 50,000 and 150,000 pixels, whereas POLLUX Panorama with a pixel size of 37.5 times 150 micrometer features a pixel array with more than 1,500 pixel columns, so the equivalent of more than 1,500 strips in a strip detector. While it still is a 2D detector, with all the capabilities of a 2D detector, you can apply an electronic aperture, or you get information on sample quality and properties, such as grain size, texture, and so on. And in addition to the full-frame 2D mode of all the POLLUX detectors, you also get 1D and 0D readout modes with region of interest. Just making the pixel finer, does this actually improve the resolution? Or is it just a different number in the spec sheet? Of course, we carefully characterize this. So my colleague Giuseppe Montemuro, one of our detector physicists, carefully characterized first the 75 micrometer square pixel size. What you see here is the line spread function acquired with this pixel size, and what the line spread function tells you, kind of an illustrative explanation, is when you have a very fine pencil beam or an extremely fine signal impinging on a certain pixel at a certain position with certain distance from the center of the pixel, how much of that intensity, what fraction of that intensity is captured within this pixel. And what you see here, what is like a hallmark feature of all hybrid photon counting, hybrid pixel detectors, the line spread function is 1 pixel full width half maximum, and that we have a very sharp point spread function where only when we're getting close to the pixel borders, the signal starts to be distributed between neighboring pixels. And how does this look like when we now have the pixel size, the pixel width? We still get this close to perfect line spread function with 1 pixel full width half maximum. So POLLUX Panorama High Resolution gives you twice the 1D resolution compared to POLLUX with the standard 75 micrometer square pixel. Yeah, what are the other features of the POLLUX family of detectors? One hallmark feature of the POLLUX family is its outstanding count rate performance and the high dynamic range that you get. The maximum count rate of POLLUX is 10 million counts per second and pixel. Yeah? So you multiply that with all the pixels in the pixel column or in the area of interest. And of course, there is nonlinearity at such high count rates. However, that is the range where we can perform an accurate count rate correction to give you accurate intensity measurements. And many detectors out there, they struggle to offer both high dynamic range and high energy resolution at the same time, because this is a challenge for HPC detectors. However, we have tackled this challenge, and we have approached it in a bit of a different way by not over-optimizing the detector completely towards energy resolution. So in combination with these high count rates and this huge dynamic range, we achieve an energy resolution better than 600 eV full width half maximum, as you can see here in this characterization experiment, where we have a fit of 460 eV full width half maximum. So POLLUX combines both high count rates and dynamic range with excellent energy resolution. And with such high energy resolution, what you can do is you can separate your kappa K alpha signal from fluorescence backgrounds, such as iron fluorescence, as you see here, the iron K alpha and beta peaks. And my colleague Hans will show you application examples how this is useful. In addition, to the high energy resolution, there are two thresholds. So you can have an energy windowing with two adjustable threshold energies. You will only count photons within this given energy range. And of course, low energy background is suppressed, as well as high energy background, like from the Bremsstrahlung radiation in your spectrum. And that way, you get better signal to noise and better data thanks to the background suppression. POLLUX also covers a wide energy range. It's calibrated for use with photon energies from 4.5 to 12 keV and threshold energies from 2.7 to 12 keV. And thanks to the 320 micrometer silicon sensor, it provides also high quantum efficiency and sensitivity for fast measurements over a wide range of X-ray energies. How about the frame rates? POLLUX achieves 360 Hertz not only in 0D and 1D mode, even in 2D full frame mode. And that in combination with zero dead time continuous readout, which is great for continuous scans when you're continuously moving your detector. You want a fast readout in order to avoid motion blur and smearing of your signal and to maintain a high angular resolution in your measurement. And that's what POLLUX delivers. Then, POLLUX is also very compact, yeah, as you can see here. It's optimized to fit into compact instruments, benchtop instruments, portable instruments, and such. It's passively air-cooled. That is the simplest and most reliable way for cooling a detector. You hook up the compact POLLUX detector with a single cable to a control unit, and with this control unit, you can control up to 2 detectors. So POLLUX is very easy to integrate, install, and operate. It's a passively cooled detector, yeah? And that can be a challenge for hybrid photon counting detectors. For many detectors, that is a challenge, so we took great care when designing the POLLUX ASIC to provide temperature-stable operation. And also this we verified during the development. So this POLLUX detector, calibrated at 23 degrees Celsius, we operated at different temperatures from 18 to 35 degrees Celsius. And when you then do a fluorescence scan, you see that the peak positions you get is always at the correct position of the 8 keV that you expect from a copper sample. So this means independently of the operating temperature of the detector, you always get accurate results because the calibration is always right over a wide temperature range. So I'd like to summarize. POLLUX provides optimal energy resolution for effective background suppression, superior count rates, and high dynamic range. It also offers a large active area, in particular for the POLLUX Panorama with 58 by 40 millimeters, and it gives you all the versatility of a pixel detector with 2D, 1D, and 0D readout modes. And now I'd like to hand over to William Boyer from Proto. Proto, they have already received a POLLUX prototype and had the opportunity to test it in their lab.
Thank you, and I just want to emphasize that I'm with Proto. We are DECTRIS customers. I'm not DECTRIS. So we make primarily X-ray diffractometers. Our history is in diffractometers designed to measure residual stress. In the last decade and a half, we've broadened that into other types of instruments. We have offices all over, and I want to emphasize I'm very thankful to our European rep based in Poland because he is at a Polish diffraction conference right now, so I got to come here from the United States a little bit outside where they usually send me, so I'm very thankful for him. Like I said, we have instruments designed for residual stress, powder diffraction, benchtop diffractometers, single crystal orientation, other instruments. One that I think is really neat is the, well, we focus on custom instruments, okay? And you can see a variety of them here. Some portable, some neat things for measuring residual stress. single crystal orientation, powder diffraction is probably what you're most interested in here, benchtop, medium size, and full size lab instruments. If it's got an AXRD name on it, it's a powder diffractometer. We have advanced things. And notice right here, this is a mythin detector. This is DECTRIS product in a lot of these. There's another one on the top right. You can get our systems in a lot of different configurations for different purposes. You can tell what that is, can't you? So a lot of different purposes, custom X-ray systems. We are the North American distributor for the Excelum's metal jet. You probably don't care about that because none of you are North American, but just want to get that out there. We do custom systems, and the metal jets usually have a DECTRIS detector in it. Yeah, so it's a lot of different things you can do with a fancy source like that. There's a DECTRIS in there too. So metal jets is, again, that's neat stuff. You can see a DECTRIS in there too. Another view of the metal jet system. All right, I'll keep going. Now we come to DECTRIS. I included a drawing and a photo of it, but it's good that Marcus showed you what they look like. Again, we got an advanced preview of what they can do. We didn't get to keep it, and we haven't fully characterized it yet, but there's a few characteristics that we are sure of. What we have here is a global mirror. Oops. Global mirror. Here's the direct beam, and you can. This is a mythin, so you can see it's saturating at about 2.5 million counts per second. That's in an 8 millimeter wide strip, and this is different power levels. The mirror's beam, you can see that increasing. Similar setup. You can. Here's the low level because this group of data is like these. So the vertical scale is vastly different. Where it was saturating with the mythin, with the POLLUX, it continues to increase in count rate all the way up to the full power of that X-ray generator. I covered over the vertical scale here because our software wasn't properly integrated, so that it wasn't really right. But it's showing you the saturation count rate is really high. It's similar to what the mythin had per pixel. So around 1 million counts per second per pixel. But the pixels are way smaller. So instead of an 8 millimeter wide strip, you've got 2D. So the count rate is really much higher. And this can be useful for, well, you might think in a lab instrument, you don't really need it. But here is a setup for XRR, where it's a parallel beam created, and then on the detector side, another mirror just like that, run in reverse, focusing a millimeter wide parallel beam down into 1 or 2 pixels. So there are times when you want a high count rate capability in a lab instrument. Again, this is because we just had a prototype thing. We haven't fully systematically characterized it. What we've got is a copper source with a mythin detector with a 191 millimeter radius. And we've got a cobalt source with a mythin with a smaller radius, and then a copper source with a POLLUX compared with a larger lab instrument. But the overall picture here is that copper radiation gives you a high fluorescence background. That's just a nature of a thing. Oh, and this again, this is iron oxide. So everybody should expect to have a high background there. But the Mythin's lack of an upper level threshold means that there were kind of two things working against it in its background, which the POLLUX improves on. So even a copper source with an iron-containing sample, you get a nice low background. And I thought I would zoom into a couple of features of that, just showing how much lower the background is. And one more here. Of course, everybody knows background is important. You can't even see this peak is here on the other data. Even though the noise is comparable, low background is just very important. It's nice to have it. It's essential in many cases. So this will give us lower background, even on iron-containing samples with a copper anode, which isn't the way you ought to do things. You ought to use a cobalt anode. Yes, beta filters. This is my last subject. We're used to having a nice K alpha peak, K alpha 1, K alpha 2. There's a beta peak somewhere over here. By the way, artifact of the fact that our integration wasn't done, this is channel number. That's the kind of thing we're used to seeing. But what if I displayed it like that? You'd think, well, where's the rest of the intensity? The fact is, this is without your beta filter. This is what we're used to seeing. Beta filter is costing us half of our desirable intensity in order to get rid of the extra peaks. So we really pay for that signal cleanup, but we don't think about it. It's just a fact of life. With the POLLUX, it's not quite good enough energy resolution to completely get rid of the K beta, and that's not what they're claiming that it can do. However, my idea is, and they seem to be running with it too, we could use a thinner beta filter, suppress some of it with the beta and some of it with the improved energy resolution of the POLLUX, and improve our intensity and still get rid of the beta signal by using a thinner beta filter. So it uses the advantages of the detector and optimizes some things. I think that's about the end here. And here's a slide just because it's got me in it. Proto's claim to fame is we will customize things for you. Should toss that in there. And it's been a pleasure working with DECTRIS people, and we look forward to getting our hands on more of this product. We've got our order in, so if you want one, place an order with us. I guess you can place an order with them too, but they're coming along soon.
So hello from my side. I will tell you a bit more about the fluorescence suppression with POLLUX and how to quantify it a bit further. And just to get everybody, we also have quite a few students attending, up to speed on how hybrid photon counting works. I'll quickly give an introduction on that. So as you know, and as Tilman explained, we have a sensor layer, which is a semiconductor layer that yeah, is very high in resistivity. X-ray photon hits, there's a photoelectric effect, it separates some charge, and there's a pulse going through the sensor layer, and it travels down through a tiny, tiny indium ball into the readout electronics, which is situated right below the sensor layer and is pixelated just like the sensor layer. So you have hundreds, thousands of tiny little detectors on your active area. Then there's the comparator, and if there's many photons coming in, like elastically scattered, the blue ones that we want to see, then there's a redshifted one with lower energy and a higher energy. This causes a proportional signal in the sensor with a bit of background noise. But instead of just adding all the signal up, there's the capability of having energy thresholds, which, if they are exceeded, fire a digital counter. So if we put them above the energy that we don't want to see and window out the energies that we do want to see, we will only measure those in a digital counter. And every single pixel has 2 of them instead of 1. So if one of them writes, the other one reads, and they alternate between each other so fast that you have a completely continuous measurement and don't lose any photons during your scans. So to summarize, with the 2 counters, you get a continuous readout and don't lose any signal. Because the counting is so fast digitally, you can count 1 million photons in every pixel every second, so a dynamic range of 10 to the power of 6, and you don't have any readout or dark noise, because all the noise that is present in the sensor will just be rejected by the energy threshold. Yeah, and how do we use it for fluorescence suppression? We did the very first test at the GNR, and Giacomo is sorry that he can't be here, but he gives his best regards, and we used the Explorer instrument and also analyzed a hematite sample, which has a natural high abundance of iron, so it causes a lot of iron fluorescence that isotopically hits the sensor and causes a big background, as Müller mentioned, with K-alpha and K-beta photons that are lower in energy than the copper K-alpha photons, the elastically diffracted that we want to see. And if you then measure this at the default setting of the detector, at an energy threshold of 4000 keV, the iron fluorescence is of course higher, and you will still see this in the background. And if you look at the picture that you see on the 2D image of the detector, you have a huge background in the back and the signal in the middle, all 1D integrated, looks like this. And this is not shifted up like you've seen in a lot of slides. This is just the genuine background of 100 counts per second. Then you increase the lower energy threshold to 7.4. You cut away the entire energy background, you retain a strong signal, and yeah, you get much better data quality. To quantify this, we have scanned the entire energy threshold range, and this is best quantified with the peak-to-background ratio, so dividing the peak intensity by the background level, or by the signal-to-noise ratio, which is the integrated peak intensity divided by the square root of the background intensity according to Poissonian statistics. And if you then normalize this to, if you do this at 4 keV, and all of this data is normalized to the standard setting of 4 keV, so you have a relative peak-to-background ratio and signal-to-noise ratio of 1, you increase the threshold, and then the peak-to-background ratio in black will rise as well, up to a factor of 40, so it's not a peak-to-background ratio of 40, it's 40 times higher than without any threshold fluorescence suppression. And same, the signal-to-noise ratio rises relatively, so you get a really high signal-to-noise ratio, which is 4.7 times higher than in the default setting of the detector. So you record the exact same position, the exact same diffraction pattern, but just with the energy the detector settings, you can make your measurement 4.7 times better. Okay, and this is really important if you want to see tiny peaks side phases, like corundum we mixed into hematite, and corundum is a really weak scatterer. So if you have the regular setting, you just get this funky signal with a signal-to-noise ratio of 1.8 that I had to fit with a lot of restraints to keep the pseudo-fogged functions there. And then when you apply the energy thresholding, you get a signal-to-noise ratio of 6.3. You see the K alpha 1 and 2 peak, and yeah, you get a really nice signal. And this could work for any minor phases that you can imagine. What else you can do is not just suppress fluorescence, but also the entire K alpha energy. So you can get rid of your nickel filter and just measure with the K beta energy, because lower energy suppression works quite well with POLLUX. So here we have the silicon 111 reflection without a nickel filter on a Bragg-Montano instrument, so you'll see K alpha and K beta peak. And then here on the left you can see the same plot basically to theta. Then the energy threshold setting on the y-axis and the number of photon counts in the third dimension. And as you start increasing the energy threshold, suddenly the K alpha 1 and 2 peaks disappears beyond the 8000 keV. And then, yeah, if you go further until 9000 EV, then you will also suppress the K beta signal. But if you go in that sweet spot at around 8.5 keV, you get completely rid of the K alpha signal and can measure diffraction with only the K beta peak, which, as it's not split so much like the K alpha peak, K alpha 1 and K alpha 2, you get a much more narrow signal, so you can potentially use it to analyze complex sample mixtures. Yeah, so in summary, POLLUX offers a higher energy resolution for X-ray fluorescence suppression and potentially cleaner data in K beta mode. So get your POLLUX now, approach our friends and from industry, our friends for the instrument manufacturers, or contact us directly if when you're interested. Thank you very much.